Okay, so thanks a lot for the invitation. It's a real pleasure to be back at CIRM. I forgot to write the title, so I'll talk about capacity for branching random walks and high-dimensional percolation. So this is joint work with Amine Asselah and Bruno Schapira, and they're both sitting in the first row. Okay. Okay, so the goal of my talk today is to talk about some recent results. The paper was posted back in September, October. So what we did is we defined the notion of capacity for high-dimensional percolation. So in my talk, I want to talk about this new notion, and I want to draw some analogies with work on branching random walks. So to start with, I'm just going to fix some notation and define the model of bond percolation. So bond percolation on ZD. So for this model, what we do is that every edge E of ZE is declared to be open with probability P and closed with probability 1 minus P. So P is a parameter in 0, 1. So with probability P, we keep the edge, and with probability 1 minus P, we don't keep it. And we do this independently for different edges. And a classical result due to Brownian and Hennenfent from the 1960s states that if dimension D is greater than or equal to 2, so dimension 1 is degenerate for this model, then there exists a phase transition. So there exists a critical threshold, PC, which is dimension dependent, PC of D, and it's non-trivial, so it's strictly between 0 and 1, so that if I write C of 0 for the cluster of 0, so the set of vertices that are connected to 0 via open paths of edges, then, and I write theta of P for the probability that C of 0 is equal to infinity, then when P is above PC, theta of P is strictly positive, and when P is below PC, theta of P is equal to 0. So in the supercritical regime, we have a positive probability for 0 to be part of the infinite cluster, to be part of any infinite cluster. And so it follows that there's going to be at least one infinite cluster somewhere on ZD with a probability 1. And it turns out that this cluster is also going to be unique. And below PC, there is no infinite cluster with probability 1. So we understand supercritical and subcritical relatively well. But what is much less understood is the critical case. So question, what happens at criticality? So here I mean, i.e. when P is equal to the critical value PC. So we know for D equal to 2 due to work of Kesten, and it uses very heavily the planarity of the two-dimensional lattice, that PC is equal to a half, and we also know that the function theta, which is a function of the parameter P, is continuous at a half, so theta of a half is equal to 0. But higher dimensions, D greater than or equal to 3, are very hard, and much less is known. And one of the central problems in percolation theory, for instance, is to show the continuity of the percolation function at the critical value, even for dimension 3. So low dimensions, 3, 4, 5, and so on, are not well understood, but much more is known for d greater than or equal to 11. So why is this the case? So this is due to a very powerful technique, which was introduced by Hara and Slade. And then there were later refinements by Fitzner and van der Hofstede. So this technique is called the lace expansion. And what the lace expansion gives, okay. Okay. So let me first introduce some notation. So if we have two vertices, x and y, I'm going to write that x communicates with y for the event that there exists an open path of edges connecting x to y. And what the lace expansion gives is that at criticality, the probability that x and y are connected is asymptotic to some constant that depends on dimension, divided by x minus y to the power d minus 2. And this is valid as the distance between x and y goes to infinity. So using this two-point function, one can get immediately that theta of Pc is equal to 0. So we have the continuity of the percolation function in high dimensions. So initially, Hara and Slade obtained this asymptotic for d above 19, and then later, using a more refined approach, it was brought down to d greater than or equal to 11. But this is expected to hold all the way down to dimension 7. And let me say that there are some recent developments by Hugo Duminil-Copin and Romain Panis, who obtained the same asymptotic, but using a different method, so it's not relying on the lace expansion. Their goal, I think, is to go down to dimension 6, but as far as I know, they still have the barrier of dimension 11. Okay, so we know now the two-point, so this is called, I will be referring to this as the two-point function. So we know what is the probability that 2 points are connected, and then using this, about 15 years ago, Cosma and Achnias studied the one-arm exponent. So what do I mean by this? They asked, what is the probability that 0 is connected to the boundary of a ball of radius r around it? So I just mean that there exists an open path of edges connecting 0 to the boundary of this ball. And so using the two-point estimate, so they assume that this holds. So as long as this holds, they were able to show that this is of the order of 1 over r squared. So I call this the one-arm estimate. And let me just say something, because I will be using this notation quite a bit. So what I mean by this notation is that there exists universal constants, C1 and C2, so that this probability is upper bounded by C1 times this number and lower bounded by C2 times the same number. Okay, so this was a very important work. They introduced a lot of nice machinery as well. And so what we understand now is what is the probability that 2 points are connected, and we also understand what's the probability that 1 point is connected to distance r. So with Amine and Bruno, we asked the following question. How about the probability that X, instead of asking for X to be connected to the boundary of a ball around it, we asked what is the probability that X is connected to some set A. So let me take A to be a subset of ZD, finite, and let's assume that it contains 0. So we move it to be close to 0. And what we want to understand is what is the probability that I'm going to take X to infinity. So I want to know if X is large, has a large norm, what is the probability that X connects to A? So this is a function of X and A. So the question is, how does it depend on A and X as X goes to infinity? Yes. Okay, yeah, good question. So from now on, I'm always working the case where we have the 2-point asymptotic. So we know that the probability that X and Y are connected, once we have this, we can do everything. So yeah, so I'm just assuming, let me put a star. So everything is under this. So the question is, we are asking now for the probability that X connects to a faraway set A, and want to understand how this depends on the set A and also as a function of X. So we would like to define some notion of the size of the set A. So we were looking for some notion like what one calls the Newtonian capacity in the case of a random walk. So before I talk about our results, what I would like to do is to take a step back and talk about simple random walks that everybody's familiar with, and actually I'm going to use a lot of things that Irina defined this morning. So simple random walk on ZD, and I'm going to consider D greater than or equal to 3, so we are in the transient dimension. So Xn is going to be my simple random walk. And because we're transient, if we start from X and we count the total number of visits to another point Y, this is going to be finite. And this is what Irina also called the Green's function. She had a capital G, but I want to have a small g. Okay, so that's the Green's function. And let me define here. So now A is going to be again a finite subset of ZD. So standard notation, HA is going to be the first time that the random walk enters the set A, and HA plus is going to be the first return time to the set A. And let me write the well-known asymptotic for the Green's function. So g of x is asymptotic to CD divided by x to the d minus 2, and this asymptotic is valid when x goes to infinity.
Right, gx, you mean like g0x?
Yes, yeah. And so what I want to say here is that this constant CD is the same as the constant that appears in the 2-point asymptotic for percolation. So we get exactly the same Green's function. And what is the analogous question for random walk? So here we want x to be connected to the set A. So for the random walk, what we want is what is the probability when the walk starts from some x far away that it hits the set A. And we want to express this probability in terms of some quantity for the set A. So how can we express this? So this is given in terms of what is called the Newtonian capacity of the set A. So there are many equivalent definitions of capacity. I'm going to give two probabilistic definitions and an analytical one. So let me start with the first probabilistic definition. So let me define the capacity of the set A as the sum over all points in the set A of the probability that starting from the point A, we escape the set A forever. So that's the first definition, but my goal is to relate this probability to the capacity. And I don't want to write it directly, I just want to derive it because it's a one-line argument. So what we want is the probability starting from X that we hit the set A. And remember, we are in dimensions 3 and higher, so the walk is transient. And so if we want to hit A in finite time, this is the same as saying that the last time that we are in A has to be greater than or equal to 0. So if I sum over all the possible times that could be the last time that we are in A, and I sum over all possible locations at this time, what I'm going to get, so A is going to be the location that we are at the last time we are in A, then afterwards we want to avoid the set A forever. And then the remaining part here is going to give me exactly the Green's function between X and A, because we just count all the visits to A. So this is called the last exit decomposition formula. And as you see, it's elementary to prove because of the Markov property of random walk, but it turns out to be extremely useful. And unfortunately, for the other models that I will speak about, they lack the Markov property. So then a lot of things become much harder. So if I now divide both sides by g of x, and I take x to infinity, because of the expression for the Green's function, this is going to go to 1 as x goes to infinity. And here we have a finite sum. And so what we get is that the limit of the probability of hitting A normalized by the Green's function is going to converge to the sum over all A of the escape probabilities, but this was defined to be the capacity of the set A. So the capacity of A that we defined in this way also appears as the limit of the hitting probability normalized by the Green's function. So that's the second definition. And finally, let me give you the variational characterization. So let me first define the following set, gx minus y, mu of x, mu of y, over all mu probability measures on A. So let me consider this set, x, y, in the set A. So I'm going to denote this as the energy of the measure mu. And if I now define EA to be what we call the equilibrium measure of A, so it's supported on the set A, and it's given by the escape probability. And then I normalize it by the capacity to get a probability measure. Then if I plug this into here, then using the last exit decomposition formula that we just saw, we get that this is equal to 1 over the capacity of A. So substituting the normalized equilibrium measure in E of mu gives us 1 over the capacity. And then using the Cauchy-Schwarz inequality for the inner product defined by the Green's function, what you can show is that when you take the infimum and you invert it, this is going to be equal to the capacity of the set A. So that's the final expression that I want to give for capacity. Okay, so I started with the high-dimensional percolation, and then I gave you the two-point asymptotic, which is the same as for random walk. My question was, how does the probability that x connects to A depend on x and A? And so you might think that, critical percolation and the random walk, they have the same Green's function. So maybe we would expect the probability that x connects to A to be related to the capacity of the set A, like we saw for the random walk. But this turns out, of course, to not be correct, because what is actually expected is that high-dimensional critical percolation clusters are expected to resemble, to look more like trees with very few cycles. So they don't look like random walk ranges, but instead what best approximates them is branching random walk ranges. So let me now define what I mean by a branching random walk. So a branching random walk is a critical branching random walk. So a branching random walk is a random walk which is indexed not by the positive integers, but instead it's indexed by the vertices of a tree. And criticality refers to the offspring distribution of the tree that I'm going to consider. So let TC be a critical Galton-Watson tree. So critical here means that the mean of the offspring distribution is equal to 1, and we also assume that has finite variance. So we are given a tree. I'm just drawing some realization. And now I want to define the branching random walk indexed by this tree. So what I'm going to do, so let me call the root like this, and I'm going to assign x in ZD to the root. And so I'm going to define my branching random walk as S and indexed by the vertex of the tree. So S of the root is going to be equal to X. And now what I'm going to do is for every edge E, I'm going to take independent random variables, XE, which is going to be uniform on the plus-minus basis vectors EI, I from 1 up to D. So XE is an IID simple random walk in ZD increment. And if we have a vertex U here, then how do we define SU? SU is going to be X, plus I'm going to take the geodesic from the root to this point, and I'm going to add up all the random walk increments along the edges on the geodesic. So it's going to be the sum over all E in the path from the root to U of XE. So this is my branching random walk. So I denoted by TC the tree, and so we denote by TCX superscript X to be the range of this walk S. So what is TCX? It's the embedding of TC into the D-dimensional space. So okay. So just like we did for random walk, we can also ask here similar questions. So what is the probability that the range of the branching random walk intersects a set A? So A is again a finite set, and we can ask what is the probability that TCX intersects a set A. If we divide this by g of x, again, the same Green's function. So why is it the same Green's function? It's because, so what is the Green's function for the branching random walk? If you count the total number of vertices that visit a given vertex in ZD, so the total number of vertices of the tree, all the u's, so that SU is equal to y, then by criticality, so the fact that the mean of the offspring distribution is equal to 1, you're going to get that this is exactly equal to the Green's function for random walk. So that's why here the scaling is the same as for the random walk. And now if you send x to infinity, Zhu showed in 2016 that this limit exists, and he called it the branching capacity of the set A, so it's just some function of the set A. And so you might wonder, here we rescale by g of x, so does it mean that the branching capacity would be similar to capacity? But it turns out to not be the case. They're totally different, the branching capacity and the Newtonian capacity that I defined. And so let me give you another definition for the branching capacity, which will make it clearer why perhaps they are different. So here I considered a critical tree, but instead of the critical tree, what one could also consider is T infinity, which has the law of the critical tree conditioned to survive forever. So let me write it. So the law of this is the law of the critical tree conditioned to have infinite size. Of course, one has to make sense of this conditioning, and this was done by Kesten. What this tree looks like is it basically consists of a semi-infinite line, and then of this line, you have critical trees that are hanging. And so if we now ask, so now we have an infinite tree, but we do the same procedure. We assign IID random walk increments to the edges of the tree. And so if we ask now, what is the probability that the range of this intersects the set A? Now we need to divide here, not by the Green's function. So here it would be x to the 2 minus d, but here we need to divide by x to the 4 minus d. And I need to multiply by a constant that depends on dimension. So what Zhu showed is that this also converges to the same quantity, the branching capacity of the set A. So we have two definitions of branching capacity, and actually he has some more. But from here, you see that the branching capacity actually, you see the 4 minus d here instead of the 2 minus d from before. So this maybe gives an indication that maybe the correct, the correct thing to do here would be to take a different kernel. So I'm defining G gamma. G gamma of x to be 1 over x to the gamma. And before, we showed that the Newtonian capacity corresponds to the choice of gamma being d minus 2. And so here, one would expect the correct gamma to be d minus 4 instead of d minus 2. And this is something, so let me say that for this discussion here, we have to take d greater than or equal to 5 for the trees. Otherwise, you see that there is a problem for dimension 4. And so with Amine and Bruno, we're able to show actually that indeed the branching capacity also satisfies a variational characterization, but we're not able to obtain it exactly, but up to constants. So the branching capacity of a set A is upper bounded by some constant times the d minus 4 capacity of A, and it's at least C2 times the d minus 4 capacity of the set A, where the constant C1 and C2 are universal over all sets A. Maybe I'll write over there. Okay, so is everything clear so far?
What is the C?
Sorry, I meant cap. So as I said, there is this heuristic that has been around for a long time that critical percolation clusters should look like the ranges of branching random walks. And so given this analogy, what we would expect would be the question for percolation to be related to the question for branching random walk. So let me go back now to percolation. And so let me state our first theorem. So our first theorem says the following. So we wanted to understand the probability that X is connected to a set A. If we divide this by G of X, what we showed is that this limit exists, and we define this limit to be what we call the P capacity of the set A. So that's the definition of the P capacity. We show that this limit exists, and then we define this to be the P capacity. So this is not particularly hard to show that this limit exists, but what we're interested in is to understand this quantity. So, so here you see that we scale first by x to the 2 minus d. So the first question is, can we also prove an analogous result when we scale by x to the 4 minus d? So what should be the correct analog of the infinite tree? So in the case of the tree, it's not very hard to show that when you condition the tree to have infinite size, that you can do this conditioning properly, and you can show that you can make sense of this law. Now, in the case of percolation, this becomes a much, much harder problem. And this is what is called the incipient infinite cluster, IIC. So here, what we want to do is to take a critical percolation cluster, say the cluster of 0, and we want to condition 0 to be connected to a faraway point x, and we want to send x to infinity. So this was first made sense of by van der Hofstad and Antal-Yarai. And they used the 2-point asymptotic, but they also had to redo Lace expansion to show that this limiting measure exists. With their proof, they could only show that if you condition that 0 is connected to a faraway point, and you take the limit, that this gives you, that this converges. But if you were conditioning instead that 0 is connected to a faraway set, then their proof would not work, because the Lace expansion is quite tricky to get to work. But more recently, actually last February, there was a preprint on the archive by Chatterjee, Chinmay, Hanson, and Soso. It's a really nice paper. And they, without using Lace expansion, just assuming the 2-point asymptotic, they showed that any construction of the IIC gives rise to any limiting procedure, gives rise to the same measure. So not only if you condition that 0 is connected to a faraway point, but even if 0 is connected to a faraway set, and more generally, if 0 is connected to a faraway set and it's required to avoid some other set, it still gives the same measure. So let me write now C infinity of x for the IIC of the point x. So I condition x to be connected to a faraway set, and I send this set, or to a faraway point, and I send this point to infinity. This is going to be the incipient infinite cluster of the vertex x. And so our second theorem asks for the probability that the incipient infinite cluster of x intersects a set A. And now we want to rescale by x to the 4 minus d, as opposed to 2 minus d from before. And so what we showed is that this, for x large, this is also equivalent to the same notion from there, the peak capacity of the set A. So here, unfortunately, we cannot show that the limit exists, but we show that lim sup and lim inf are up to constants, the peak capacity. But actually, even when A is just a single point, it's not known that the limit exists. Okay, so now we would like to understand what type of capacity peak capacity is. And we would expect it to be equivalent to the branching capacity, which is equivalent to the d minus 4 capacity. What we are able to show is that the peak capacity of a set A is always at least some universal constant times the d minus 4 capacity of A for any A. So we always have this lower bound, and I think I'll give you the proof of this. So in particular, what we prove is that the probability that X is connected to a set A is at least, let me put C times the Green's function times the d minus 4 capacity of the set A, as long as X is like twice the diameter of A. So we have this lower bound. We expect it also to be an upper bound, but we can't prove it yet. But what we can prove is, okay, yeah, let me just write the last theorem. We don't have an upper bound, but what we know is that the peak capacity of a ball of radius r is r to the, of the order r to the d minus 4. So this agrees with what the d minus 4 capacity would be, but we only know it for balls. So in the remaining time, so how much time do you have? Okay, great. So what I want to do is I want to explain this lower bound because it's a very simple argument, and it turns out to be quite useful, even though it's so simple. So let me say why it is useful, for which cases it is useful. So let's suppose that A is a sparse set. So I'm not going to explain exactly what I mean by this, but I just want to say that we mean that the intersection of A with any ball of radius r centered at A is going to be much, much smaller than the size of the ball, the volume of the ball. So if we have a sparse set A with a correct condition for sparsity, then from the variational characterization, we can get that the d minus 4 capacity of A is going to be at least some constant times the size of the set A. So this follows immediately. Once you have the correct condition here, you just go to the variational characterization and you get this lower bound. But of course, we also have an upper bound of the size of A for the capacity. And so what this is saying is that if A is a sparse set, then this lower bound here, X connects to A, is at least g of X times the size of A. And it's also upper bounded just by a union bound by g of X times the size of the set A. So for sets A that are sparse in a certain sense, what we get is that we get exact asymptotics up to constants for the probability that X is connected to the set A. So what I will do now is, let me bring a board down, or maybe I'll erase here. I will explain the proof of the lower bound. So the proof of this lower bound for the probability that X is connected to the set A uses an idea due to Fitzsimmons and Salisbury. They used it in the setup of random walks and more general Markov chains. It's a very powerful technique. It has been used a lot of times in random walk problems. So remember what we want to show. So proof that, let me write it here, the probability that X connects to the set A is at least G of X times the D minus 4 capacity of the set A. Okay, so what we're going to use is, of course, I mean, we only have the variational characterization here for this capacity. So let's take a measure mu. Let mu be any probability measure on the set A. And now let me define capital Z to be the sum over all A in A, mu of A, times indicator that A is connected to X. So I count the number of points in A that are connected to X, but I weigh them by mu of A. So now so the probability that X is connected to the set A is, of course, at least the probability that this random variable Z is strictly positive. And now, by the second moment method, or Perla-Sousi inequality as it's called, we have that this is at least the expectation of Z squared divided by the second moment of Z. So we want a lower bound on this probability, so it's enough to look at the ratio of the first moment squared divided by the second moment. So let's calculate what is the first moment of Z. So the first moment of Z is the sum of mu of A times the probability that A and X are connected. But this is a G of A minus X, so it's the sum over all A of mu of A times G of A minus X. A in A is just a fixed finite set. And so when you take X far away, this is going to be of order G of X. And so this is going to be, the whole thing will be G of X times the sum of mu of A, but mu is a probability measure, so it's just G of X. Okay, so the first moment is very easy. So let's look at the second moment of Z. Okay, so for the second moment, what we get is the double sum over all AB in A of mu of A times mu of B times the probability that A is connected to X connected to B. So we have 3 points, A, B, and X. They are connected in this way. And so it means that there will be some third point Z. So this probability, we can upper bound it by union bound. And this Z is going to be connected to each of these 3 points disjointly, so the paths will not intersect. So A communicates with Z disjointly from Z communicating with B, disjointly from Z communicating with X. So I want these 3 paths to use disjoint sets of edges. And now, the BK inequality says that if you ask for these events to occur disjointly, the probability of this is going to be upper bound by the product of the probabilities. And this is actually quite intuitive, because if you condition on these 2 events and you ask for A to connect to Z without using the other 2 paths, of course, it reduces the number of possibilities that you have, so it should make it smaller, and then you iterate. But of course, this is not so trivial to prove. It's the Vandenberg-Kester inequality. And so this is upper bound by the sum over all Z of G of A minus Z times g of z minus b times g of z minus x. Now, here we are summing over all z in zd, but let's say that since x is large, we can take this out as g of x. So this is going to be g of x times the sum over all z of g a minus z times g of z minus b. So what do we see for the second moment of z? We got g of x times this sum, but this sum is the convolution of g with itself at a minus b. So this is, okay, I'll just write here, this is g of x times g star g at a minus b. And if you convolve g with itself, g is 1 over x to the d minus 2. What we are going to get here is that this is g of x times 1 over a minus b to the d minus 4. The convolution of the Green's function with itself will give you the power d minus 4. And so, oh, I forgot to write it. Okay, so here I just upper bounded this quantity. And so the second moment of z is upper bounded by the sum over all a b mu of a mu of b times this. And so it's going to be upper bounded by g of x times the d minus 4 energy of the measure mu. And if you substitute here, you will get a g of x eventually, and you will have to divide it by the energy, and then when you optimize over all measures, you're going to obtain exactly the variational formula that I said before. And I will end my talk here. Thank you.
Thank you very much, Perla. Are there any questions?
Yes?
Regards the fact that the definition in current 1 and current 2 are directly proportional, or do you have only up to a constant?
Yeah, only up to constants. Because for theorem 2, you don't even know it if A is just a point. So if A is y, you know that it's 1 over x minus y to the d minus 4. Even for just one point. Sorry, okay, let's take x to be.
There is a 1 to 5.
Yeah, but you don't know that the limit exists, do you?
That the point is connected to the okay.
No, but it's for the IIC.
Yeah.
So I don't think this is known.
We have a paper with a much hot.
Ah, but it's not out yet.
It's not yet, but I wonder if
Okay.
you have already this equivalent.
No, we don't. Ah, so you do have this equivalence now.
Yeah, but it's in a big paper with a
Yes.
limit of
Yeah, I know. Okay, I see.
Other questions?
Yes?
So for this expansion, is there necessary to work on discrete staging? What about any continuous version of this expansion?
To be honest, I'm the wrong person to ask because I am not an expert at all on lace expansion. So I don't think they can. I'm not sure I fully understand the question, but I don't know if it can work in the continuum.
Does it let them work the Brownian motion
Yes.
and the singular branching Brownian motion thing?
Well, but lace expansion is used for percolation, not for the random walk.
So I know people use this expansion to work on self-avoiding.
Okay, yeah. Yeah, I don't think it's. Yeah. I mean, also, how do you define the self-avoiding? Yeah, okay, sure. Yeah. No, but I don't think it's been used. Yeah.
Perhaps I missed it. That you have this result that you said it was two for big dimension bigger than 5, but the one above is for lower dimension as well.
No, everything is for, yeah. So I should have said at the beginning, for branching random walks, I'm working dimension 5 and higher. Otherwise, the scaling is different.
Other questions? Okay. No, let's
Thank you.
thank you.
Thank you.